this is just a recording of how we can solve a very specific sort of excellence problem. Some background first. If we take a point and we take a distance from that point, and then we plot all the points that are the same distance, then we generate a circle. That is what a circle is. It's all the points equal distance from a single point, and the distance out is given as the radius. Well, we can also do that, but from 2 points. So if we plot a point that is distance A and B, and we keep the sum of A and B the same, so that when added together they add up to the same amount, then we generate an ellipse. You don't need to know that, but that is the shape generated, and if you do Year 13 calculus, then you will get to do the maths of it. Effectively, it is a stretched circle. So how does this matter for our trig? Well, if we take a quadrilateral and we keep the perimeter the same but move one of the points, then the shape that we are generating is that ellipse. Given 3 fixed points and 1 point moving, but the perimeter adding up to the same amount, generates an ellipse. That ellipse has various zones, make quite a difference to the shape that we get. So I've coloured them in various colours. Let's just look at some of them first. The red one, that's where the quadrilateral is in fact no longer a quadrilateral because it's crossing over itself. So on either side, on the outside at the bottom, we just don't have a quadrilateral. So that doesn't really come into play, and we can ignore them. The purple down at the bottom is when the top angle is inverted, so we get more like a kite shape, and again we're very rarely interested in that. So what tends to matter is the bits on the top half of the ellipse, and there's 2 zones. The ones I've coloured yellow is where the angle on the interior now exceeds 180 for one of the points. Technically, this is now a concave quadrilateral because it flexes the unusual way. And it's the same on the other side. This time the concave angle is at B. So the green zone is the bit where we still have the constant perimeter, but we don't have the quadrilateral extending outside of 180 degrees for any of the interior angles. So we want to work out where that starts and where that finishes. Well, it starts and finishes when this point drags so close to there that in fact we've got a straight line along ADC. We no longer in fact have a quadrilateral, we have a triangle. Any point further than that, then the angle at D will start to exceed 180, and it's the same on the other side. At any further point than the straight line, the angle at B will start to be more than 180 degrees. So let's put some numbers in and see how we can do the maths. I'm going to have a quadrilateral of constant perimeter, and these are the numbers we start with, and we're going to keep the lengths of 9 and 12 fixed and vary the ones of 7 and 8, but so they always add up to 15. So let's do the left hand side first. We straighten the quadrilateral so that this line is straight, and so the line which was 9 now has an unknown extra distance, let's call that x, and so that side length of the triangle is now 9 plus x. What remains is the 15 of the perimeter less the bit we've put on that side, so the other side is going to be 15 minus x. And there's our triangle. 3 sides. We just don't know what x is yet. Well, we've got 4 pieces of information, so we can check what x must be to make this triangle true. And I'm going to use the cosine rule. I'm going to use it in the cos angle formulation, although you can use the other version of it too. So we have this must be true for the triangle. I'm going to stick in my values, so that must be true. Then it's a matter of solving that equation. This is where the trouble becomes, because you have to be extremely careful with your expansions and simplifications. So it plays out like that, and in fact it simplifies quite simply at the end to 48x over 216 plus 24x. Once we've done that, we multiply the bottom across, expand the brackets, put the x's on one side, divide across, and we get that our unknown distance is 4.525. So much can go wrong with that you're foolish to just leave it there. You should go back to the original equation, stick it in, we get that value. If I inverse cos, then I get back to 48. So I have done my working correctly because it checks out. Okay, so we'll run through that one more time. This time, instead of finding the left hand side, and now I know that any length shorter than that, and this will be more than 180 degrees. So I'm going to do it out to the other side now. So I'm again calling this distance my unknown distance x. What remains on this side is still 15 minus x. Well, 15 minus x is adding to the 12, so that side is 27 minus x. So we have my triangle. We know it's true. That means this must work. We stick in our values. But this time, instead of doing it by hand, I'm going to use the calculator. So I type my values out like that into Solver, being very careful that the top and bottom of the fractions are all in brackets. So we do that. Let's have a look at it. So there I have it typed out all the way across. I'm going to enter that. I've got a starting seed value about what I think it should be. I press solve and my solution is 11.555. So 11.555. Again, because it's very easy to type something wrong into your calculator, I go back and I check that. I take my original fraction, substitute in 11.55 for my unknown. I get that, invert cos that, and I'm back to within Kiwi of my 48 degrees again. So I know I've done it right. So that's the process. It enables us to determine the length on the right hand side before the quadrilateral starts to flex outside the 180 degrees, and I can give the answer.